So good morning, everyone. Are the slides visible? TM?
Yes, sir, visible.
Yeah. So regarding the event, like today's evening, so we have an event on Yoga Day, and the link has been sent to your WhatsApp group. So without fail, do attend that event. Okay. So we have an online event going on, and the link is being sent to your WhatsApp group. So without fail, log in at exactly 5 o'clock today evening and do attend the event. All right. All of you. So only 5 participants have logged in. Yeah. Shall we start? So this is the next algorithm. So next page replacement algorithm is LRU. LRU stands for least recently used. So least recently used page replacement algorithm. And in the last class, we had seen first in, first out page replacement algorithm. So regarding this least recently used, we are supposed to replace the page, okay, that has not been used for a long time, right? So understand this statement. You replace that page that has not been used for a long amount of time. That page you are supposed to replace. Okay. Similar to the first in, first out page replacement algorithm, like we'll be giving the list of the pages. So 5, 4, 3, 2, 1, 4 up to 2 and 1 are the list of pages. Okay. Like that has been given to us. And we have been given how many frames here? How many frames are there here?
3.
Yeah. So we have 3 frames, F1, F2, F3. And all these frames are belonging to which kind of memory? Main memory. Remember this. Like all these frames are nothing but the blocks, right? Or the memory blocks or locations in the main memory. So whereas these pages will be in the physical memory. And using this LRU replacement algorithm, I need to allocate the frames for these pages. Okay. And that like, so what policy like you're supposed to use here is least recently used. That means you are supposed to replace that page that has not been used for a long amount of time. Okay. So based on this statement, so what will be the first step? First step is to go for the assigning of the first page. Okay. And the first page is page number 5. Okay. And for that, what I can do, I can simply have the frame number 1. Okay. That will be stored in the frame number 1. Okay. So page 5 is stored in frame number 1. And obviously, like you'll be having a page fault or page hit. Here it is.
Page fault.
Page fault X. Why? Because this particular page is not there in the main memory. Hence, here we have a page fault. Okay. So again, going for the next page. Next page is page number 4. Okay. So this page number 4 can be stored in the second frame. Okay. Again, we have a page fault here. Why? Because this 4 is also not being present in the main memory. All right. Yeah. So next is page number 3. Okay. So do we have this page number 3 in the main memory?
No, sir.
No. So for that, I can store this page number 4, page number 3 in the frame number 3. And I can maintain this frame 1 and frame 2 with the pages 5 and 4 as it is. And again, we have a page fault here or a page miss. Okay. So now coming to the actual implementation of this LRU. Okay. So this page number 2 is the next page. Okay. So again, here we have a page fault because this this page number 2 is not present in any of these frames. Hence, we have a page fault here. And now the real question is which page has to be replaced? Okay, like among the 5, 4, and 3 pages. So which page has to be replaced? So for that, I need to see like the process that has not been used for a long amount of time. Okay, like on the page, like for the page that has been not used for a long amount of time, that page needs to be replaced. And for that, again, we can follow a main shortcut here. Okay, so you can just see that the page number 5 is rightly used here. Okay, and page number 4 was next used after the page number 5, and page number 3 is rightly used here. Okay, so you can just see the MSB position in the page sequence or in the page strings. Okay, and here the MSB position is for the page number 5. Hence, what I can do is I can replace this page number 5 with the new page, that is page number 2. Okay, and 4 and 3 are retained as it is. Is it clear? Earlier in the first in first out, what we did was we just observed the MSB position of these frames. Okay, right, and that was indicated using a symbol called as the flower bracket, right? Hello?
Yes, sir.
Yeah, similarly, in the least recently used policy, we are supposed to look at the page strings and we can concentrate on the MSB positions, okay, of the page, and you can replace that particular page with a new page. So for example, this next bit is 1. Okay, so next bit is 1, right? And this page is not been present in the main memory. Hence, we have here the page fault is there. And among these among these 3 pages, page number 2, page number 4, and page number 3, the least recently page reuse is, again, you can look at that. So this so-called page number 2 is rightly used here, and page number 4 was used here, and page number 3 is used after the use of page number 4. So among these 2, 3, and 4, the 4th page is at the MSB position. Hence, I need to replace this page number 4 with a new page, that is 1. And I can retain this page number 2 and page number 3 as it is. Is that clear? Is that clear?
Yes, sir.
So after this, next page is page number 4. And what about this page number 4? Whether we have a page hit or a page miss.
Page fault.
Yeah, we have a page fault or a page miss. Why? Because this particular page 4 is not there in any of these frames. Hence, I can enter here X. So next question. So which page needs to be replaced? Again, you can see that 2, 1, 3. Right? Again, see the like the given string here. So page number 1 is here, and page number 2 is here, and page number 3 is here. Okay. So when compared to page 1, 2, and 3, the 3 is at the MSB position. Hence, which page I need to replace here? Page number 3, right, is replaced with a new page 4. And I'll retain this page number 1 and 2 as it is. Okay. So next page is page number 3. Again, we have no pages there. Hence, it is a page fault. And again, you see this page number 2 is here, and page number 1 was here, and page number 4 is rightly here. So among these 2, 1, 4, the page at the MSB position is page number 2. Hence, I can replace this page number 2 with the new page, page number 3. And 1 and 4 are retained as it is. Fine. So what about next page? Next page is 5. Again, we have here
Page fault.
Page fault is, yeah. Again, we have page fault. And among the pages 3, 1, 4, 3, 1, 4, right? Among this page 3, 1, and 4, like which bit is at the MSB position? Which page is at the MSB position? 1. Okay. So for that, I can replace this page 1 with the new page 5. And 3 and 4 are maintained as it is. Next is page number 4. page number 4. So what should enter
Page
here?
hit.
Yeah.
Page.
So we have a page hit. Why hit? Because so this page number 4 is available in the frame number 4. Hence we have a page hit here. Okay. So once we have a hit means no need to replace any of the pages. Okay. Yeah. So next page number 3. Again, you can see in these frames.
Page hit.
Yeah.
Page hit.
Yeah. So we have a page hit, right? So once I have a page hit means no need to replace any of the pages. Hence, you keep the pages as it is. Now coming to the page number 2. Page number 2 is not available. Hence, it is a page fault. Yeah. So we have a page fault. So now, so which page has to be replaced?
5.
5. Why? Because 3, 4, 5. I mean, like suppose if you look at this page number 3, 4, and 5. So the fifth page is at the MSB position. Hence, I can replace this new page 2 with the page number 5. Yeah. So you can write 2 here, and 3 and 4 are as it is. Now coming to page number 1. So page number 1 is not there. Hence, it is a page fault. Right? So we have a page fault here. Now observe page number 2, 3, and 4. So which page has to be replaced? Hello? Hello, is it audible?
Yes, sir.
Yeah. So like we had a slight power fluctuation. Yeah. So now tell me. So which page has to be replaced?
3.
4.
No, 4. 4.
4. Why? Because page number 2 is here, page number 3 is here, and page number 4 is here. So among these 3 pages, okay. So which page is at the LHS MSB bed? Page number 4 it is. Hence, I'll be replacing this 4 with page number 1. And what about this page number 3 and page number 2 retained as it is. Yeah. So now we can count the number of page hits and number of page faults. So the number of page faults 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So we have the page faults as 10. So what about number of hits? Number of hits are only 2. Okay. So once you calculate the number of the page faults and page hits, next step is to calculate the hit ratio. So what is the formula to calculate hit ratio? Number of hits divided by total number of pages. Okay. So the number of hits are only 2, and we have how many pages here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 number of pages are there. Hence 2 by 12 is the page hit. So what about the miss ratio? Miss ratio is given by number of page faults divided by total number of pages. And according to the solved problem, here you can find how many page faults. How many page faults are there?
10.
Yeah, 10. Okay. So this 10 divided by total number of pages, we have again 12 number of pages. Okay. So like in the examination, they may also ask you to calculate the probability of page faults. Okay. So for that, the simple solution is the number of page faults divided by total number of pages available into 100 you do, and that comes around 83.3%. Similarly, for calculation of probability of page hits, okay, same formula. So we have number of hits divided by the total number of pages available, right, multiplied by 100, and that comes around 16.6%. Is that clear regarding LRU? I repeat, in case of LRU, you just observe the MSB positions in the sequence of pages given. That's it. And in case of first in, first out, what we did was we were seeing the MSB positions of the frame. Okay, so but here in case of least recently used, like as I have shown here, So this star indicates what? Star indicates that you should be able to see the MSB positions in the number of pages, and the page at the MSB position, that page needs to be replaced. Why? Because that particular page is not being used for a long amount of time. Okay. Yeah. Like similarly, like we have here one more sequence of strings given, sequence of pages given. So for this sequence of pages, you need to solve this using which algorithm? LRU, least recently used algorithm. And again, the small hint, small clue here is, so just remember this particular small clue and go on solving. And for this particular problem, after solving, you have to get how many page faults? 14 number of page faults and 5 number of hits. Okay, so just verify this by solving the problem and verify that whether you have here 14 number of hits and how much it is? 14 number of page faults and 5 number of hits. Okay, yeah. So next thing is again, like according to the book, like they've given you the simple table here where we are comparing the first in first out and the LRU policy. Okay, so for these many pages, and here they are able to give us how many frames? Only 2 frames have been given. Only 2 frames are being given. Okay, so this huge table is being simply shown in this form. Why? Because we are familiar with this particular format of the pages and the frame numbers. Okay, thereby we can calculate the number of hits and number of page faults, right? So here, for our easy understanding, what I've done is, like I've just written the same table where this is nothing but the first in first out algorithm being used, and here is the least recently used page replacement policy. Okay, so these tables, okay, so one for the first in first out, and this is the table for the least recently used page replacement policy. Okay, so you can compare these two tables. Okay, like they are same here, right? So for these many pages and having only 2 number of frames in the main memory, you can go for a use of first in first out algorithm and solve and calculate the number of replacements needed and the number of hits. Okay, and like as we are familiar with first in first out and LRU, okay, you try to understand this and also see that you'll be need of how many replacements. Here I'll be need of 4 number of replacements in case of first in first out, and in case of least recently used, I'll be in need of here how many replacements, how many page faults are there according to this particular figure. How do you how do you indicate page fault or a page miss? So by writing what it is, into mark, X mark. Okay, and we can indicate the number of hits by writing H or HIT for hit. Okay, and you can see that, say for the frame number 1 and frame number 2, so for the first 2 pages no replacements are needed. Why? Because as we have here 2 number of frames available, hence you can accommodate each and every page in the 2 frames available, right? And from the third amount of time, okay, select only for the 3rd page, right? I can go for the replacement to be done, right? And according to the LRU policy, you can observe that upon solving this particular problem, you will encounter how many page faults? 3 number of page faults. So when compared to the first in first out, we saw, or we had here, how many page faults? 1, 2, 3, 4 number of page faults or page replacement was done here. Okay, so you can analyze this, say for 2 frames. Okay, and for these pages using LRU policy as well as for the first in first out policy, hardly it may take you around 10 minutes. Okay, right? So you can analyze this, and if you are not following, means the next video let me discuss these 2 frames. Okay, So why I'm moving along is why, because already like we have solved two problems on first in first out and one problem on the least recently used. Okay, so when compared to this particular problem, okay, right, what we have solved, like this is very much a small problem, like having only hardly around 6 to 7 number of pages. Okay, but that you can handle easily, right? So next important topic is something called as locality of reference. Okay, so which comes into picture when we have this page replacement to be employed or used. Okay, so the basic concept here is, suppose if a logical memory address is being referenced. Okay, suppose like in a set of memory locations, if I'm able to access a logical memory address, so then nearby memory addresses will tend to be referenced soon. Okay, so what do you mean by this? A simple example of what I can give is, suppose if say like faculty is like asking some questions for the first bench students. Okay, suppose if the faculty is asking the first student, okay, and if the student is not able to answer, so then select what might be the next step taken by the faculty. Faculty may be asking, like there is full chance that, okay, the faculty may be asking the very next student sitting next to the first student, right? Have you observed that? Hello, have
Yes,
you
sir.
noticed, have you noticed that generally, usually, like the so like casual tendency is, suppose if the faculty is asking the first student, right, and if the first student is not able to answer the question, means like usually what we do is like I'll be asking the next student, like next student, right, sitting very next to the first student, and if second student is not, it is also not able to answer, means I'll just shift to the next student, right, or the third student. Okay, so by keeping this in mind, you try to understand the locality of reference. Suppose if I'm accessing a memory address, okay, so right, but then there is full chance that the nearby addresses will be accessed soon or in future. Okay, so why we assume it like this? Because of mainly two reasons. First reason is, execution of instruction in a process is usually happening in a sequential way. Why? Because whatever program you write, okay, like using any language, right, all the program are having instructions, and those instructions will be what, written in a sequential manner. Okay, hence if the CPU is accessing the first instruction, means like there are full chances that the next instruction to be accessed will be the second instruction, and after second instruction, the next instruction to be executed will be the third instruction. Okay, hence the logical memory address access, okay, is there, means there is a full chance that the next address will be accessed in the near future. Okay, and second reason is that the processes always tend to perform similar operations on several elements of a non-scalar data, such as array. Like these arrays, or so you can take the example of say some looping operations. Okay, so what happens in looping? I'll be executing the same set of instructions again and again. Is it right what I said right now? Are you following it? Hello?
Yes, sir.
Say for I is equal to 0 and I is less than equal to 100, I plus plus. Okay, like in this instruction, right, or statement. So what we do here is like I'll be executing the same instruction, same set of instructions again and again until we have the completion of the upper limit. Okay, like in that case, what is happening really is a logical memory address reference. Okay, suppose if I'm accessing the first instruction, right, so then there are full chances that after the access of first instruction, the next instruction to be accessed will be obviously the next instruction. Okay, and to understand this, the best example what I can give here is, say suppose in a class, okay, and if the faculty is asking a question for the first bench student, means suppose if the student is not able to answer for the question, so then the faculty will be obviously going for the second student in the same bench. Okay, like hope you have noticed this many times. Okay, so based upon that, so you can analyze this particular statement of locality of reference. Okay, so the instructions and data references made by a process will tend to be in the close proximity or in the same neighborhood. Okay, so this means that the faculty will be asking the questions, okay, starting from the first student, and the next student to be asked will be the second student, and after second student, obviously the faculty will be asking the third student. After third student, next student will be the fourth student. Okay, so the like the neighborhood is only belonging to the first bench students, right? So the proximity is limited to only the students sitting in the first bench. Okay, yeah. So that we call it as the locality of reference, right? So the law of locality or the locality of reference says that it indicates that the logical addresses used in an instruction, okay, understand this, the logical addresses used in an instruction is likely to refer to a page that is in the current locality of the process. Okay, suppose if it is the logical address space of let's say like any process I. Okay, so this whole solid box is the logical address available for the process I, and if this is the logical address accessed, and this shaded hashed line is indicating the proximity region of the logical address. Okay, suppose if I'm accessing this particular logical address, means the next accesses or the references will be the addresses that are very much close to the accessed address, right? Okay, so this virtual memory manager ensures that fewer page faults will arise if it ensures that the pages that are in the current locality of a process are present in the memory. So what do you mean by this particular statement? Okay, so to explain this, I like a simple example has been considered here. Okay, suppose if we take it as the main memory, okay, and if the CPU is able to access, say, this particular instruction or address, okay, right? Suppose if it is the case, means like the the next accesses will be obviously the neighborhood addresses, okay, or the neighborhood instruction addresses will be accessed by the CPU, right? Like in that case, so what we can do so as to reduce the access time, right, and to increase the speed is like I'll be storing all the neighboring instructions or the neighboring addresses in the cache memory, so that this CPU can access, right, all the instruction or all the addresses, right, from the cache. Okay, hence we are avoiding the access made by the CPU to the main memory, right, or the RAM. Why? Because like, to access the RAM, it will take more amount of time. Okay, so the access time needed will be more, hence to reduce the access time and to increase the speed, what I can do is the access instruction or the access address, right, along with the neighboring addresses can be stored in the faster memory, so called cache. Okay, right, hence in the next time, suppose if say CPU wants any instruction, means the CPU can take the instructions from the cache itself. Okay, hence again reduce the access time, thereby increasing the speed of operation or speed of execution. So this we call it as spatial locality. Okay, so this we call it as spatial locality because here we are discussing with respect to the address space. Okay, right, address space of the process, hence it is called as spatial locality. And so like we do have one more kind of locality that we call it as temporal locality. Okay, so what do you mean by temporal locality? So to explain this, like I've written a simple diagram here. Okay, where we can find here n number of instructions are there, like instruction 1, instruction 2, 3, 4, 5, 6, 7, 8, etc. Okay, suppose if the process is accessing like instruction 5, 6, 7, and 8. Okay, so these instructions 5, 6, 7, and 8 are being accessed repeatedly. Okay, are you following this? So like here we have a, right, like here we have a series of pages, okay, series of pages or instructions, okay, right? Like I need to access this instruction of pages 5, 6, 7, 8 again and again. Okay. Suppose like in case of looping, you can expect this sort of execution, right? So like where the pages 5, 6, 7, and 8 will be accessed repeatedly, right? So in looping applications, we can use so this temporal locality, that is referencing the instructions or the pages in a loop. Like as you can see here, 5, 6, 7, and 8, and again 5, 6, 7, and 8, and again pages 5, 6, 7, and 8 are accessed again and again. Hence, this can be like observed as a looping operation. Okay, so it is page 5, 6, 7, and 8 are required again and again. So if an item or like if an item or address or a page is accessed in the memory, right? So then same instruction, same pages will tend to be referenced again and again in the near future, and that we call it as temporal locality. So when dealing with the looping operations, where a sequence of operations will be happening again and again, means same operations, same function will happen again and again. In that cases, I can expect this temporal locality. And what about the spatial locality? Spatial locality refers to the access of, say, one address, means like in the next future, okay, I may be accessing the neighborhood addresses in the address space, right, available for a process. Hence, here what we do is that I'll be storing the nearby addresses also in the cache memory, okay, where the CPU can access these addresses at a much more faster way. Okay, so like regarding this locality of reference, so you can take the help of this particular figure according to your book. Okay, and also you can explain the definition for locality of reference, also called as a principle of what do you call it? Principle of locality or law of locality. Okay. So next is memory allocation to a process. Okay. So the heading for this is memory allocation to a process, right? So this shows how the page fault rate of a process would vary with the amount of memory allocated to it. Okay. So here, basically, like what we're discussing here is, the relation between the number of page faults and the amount of memory which gets allocated for a particular process. Okay, so the page fault rate is large, so when a small amount of memory is allocated to a process. So what do you mean by this? Suppose if say for a process pi, okay, so for that particular process, if I'm able to allocate a small amount of memory, means in that I can store only small number of pages or lesser number of pages. Okay, hence the rate of the page faults will be very much high, or like I'll be having large number of page faults. Okay, higher number of page faults will be occurring if the small amount of memory is allocated for a process. However, so this number of page faults, right, can be reduced if I'm able to allocate large number of memory for a process. Okay, so this virtual memory manager, what it does is, so this virtual memory manager can take some corrective actions. Okay, if it observes that a process that has a high page fault rate, okay, and so this VMM it will try to reduce the number of page fault rate. How come it will reduce? Just by increasing the number of memory that gets allocated to the process. So this VMM can take some corrective actions if it finds that the process has got a higher number of page faults. Hence, to reduce the number of page faults, what this will do is it will increase the memory size allocated to a particular process. Okay. Say, so for example, you can understand like this. See here, suppose if you have a RAM here, okay, like in this RAM, okay, so what we expect ideally is I should be able to store more number of processes inside this particular RAM. So for example, this P1, P2, and P3 and P4 are the different processes. And what about these P1, 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 P1 all these are the different pages of different process. So for example, this P1 refers to the process P1, and this P1 is the first page of this process P1. And this what about P2 comma P1? P2 comma P1 is the second process and the first page of second process. What about P3 comma P1? P3 is the third process and the first page of this process P3. Okay. And what about P4 comma P1? P4 is the separate fourth process and P1 is the first page of this process P4. Okay. So here what we're expecting is I should be able to store more number of processes. Okay. Thereby, okay, I can increase the degree of multi-programming. Okay. How to define this degree of multi-programming? The number of processes stored in the main memory or in the frames will be indicating the degree of multi-programming. And according to the say good performance, what we expect is I should be able to store more and more number of processes. Okay. Say for example, here I've taken that P1, P2, P3, P4 are the 4 processes. Okay. And only the first page of all the processes are being stored in the RAM. Okay. Suppose if now our CPU, right, is demanding for the second page of all these processes or say third page of all these processes, right? In that case, what will occur? Can anybody answer me? We have these many processes and these many pages of these processes. Suppose if the CPU is demanding for second page of P1, right, or say third page of P2 or fourth page of P3 or say second page of P4, are they available in the RAM?
No, sir.
No. Like in that case, what will occur? Page fault will occur. Is it right?
Yes, sir.
Why? So why is page fault will occur? Because the pages demanded by the CPU are not available in the RAM. Hence, page fault will occur, and you can observe that the degree of multi-programming is high. So, but the page faults are also high. Why? Because the pages demanded by CPU are not present in the main memory. Hence we have here higher number of page faults. Okay. So once we have the page faults, so then how to solve this? How to solve this means like I'll be removing any one of these pages and I can replace this page with a new page. Okay. Hence we need to waste so many time in just swapping the process from the RAM to the hard disk and from hard disk to the RAM. Okay. So even though we have here a higher number of processes to be stored in the RAM, right? I mean to say, even though we have higher number of multi-programming, right? So, but even then you can expect a higher number of page faults. Okay. So the CPU will be spending more time in just swapping the process from say from RAM to the hard disk or from hard disk to RAM instead of doing some useful work. Hence, we have the degradation of the CPU utilization. Okay. Hence, we need to maintain an appropriate ratio between the degree of multi-programming and the number of page faults. Okay. So that is the bottom line, right? So we have a like heading called as thrashing here. Okay. So what this thrashing means? So for that, you can like observe this particular figure. Okay. So what is happening here? Like along the X, like what we have considered along the X axis, like we have taken the degree of multi-programming. So what basically is degree of multi-programming? How many processes you are able to store inside the RAM? Okay. And according to say like this particular figure, right? So what you're seeing here, I have stored how many processes? 4 processes, P1, P2, P3, P4. Right? And what about these? These P1 are nothing but the first pages. First pages of these different processes. Okay. So the degree of multi-programming can be defined as the number of processes that are present in the RAM. Okay. So along the X, like I've taken degree of multi-programming, and along the Y axis, we have considered CPU utilization. And as you can see by the graph, right? Suppose if I have here higher number of processes means